People online, can you hear us? Like me? If you can give me like a quick thumbs up or write down in the chat. Yes. Cool. Thank you. Um, I think we'll begin in like next 2 minutes, just giving time for everybody to settle down. Okay, everyone, can we settle down quickly?
Audio is on. Okay, they can hear us? Okay, perfect. All right.
Okay. Hi, everyone. Good evening. Thank you so much for dropping by for this session. This is essentially session 0, or let's say the session 1, and the beginning of the fall 2025 Getting Started with Machine Learning series. This is something that we have prepared for you guys, that we have a series of 10 to 12 workshops down the line over the semester. And what we want to achieve with this workshop series is that you come in with little or no knowledge of ML and you leave with something knowledge worthy, something on the lines that, okay, ML was something for you, but once you leave the 10 to 12 sessions, like after that, you know what LLMs are, what NLP is, how machine learning works, how neural networks work. That is the thing that we're talking about. Today is the session 1, so we'll pretty much be talking about how machine learns, what is deep learning, and I'll go over the agenda in detail. But before that, let me just circle back and show you guys what is in the plan so that you guys can also prepare yourself for the things ahead. We have this up there on our Instagram. So this is the Getting Started with Machine Learning series. It's 12 hands-on session of workshop wherein we teach machine learning from the basic to an advanced level. Today's session, which is session 1, we'll talk about the broad classification of machine learning, artificial intelligence, how the landscape of AI, ML, and DL works, where and how the LLMs came into the picture, what is NLP, what is computer vision, because this will set the soil right for us. Once this is done, we'll talk about the mathematics. So a lot of people start learning machine learning, but they miss out on this particular topic. And I think this is one of the most important bedrocks for learning machine learning, because if you don't understand the maths behind it, it's going to be super, super difficult once we advance to difficult topics like deep learning and how LLMs work and all those lines. So maths is super important. So the next session that we're going to have next Wednesday is going to be all about mathematics. And trust me, you don't need to be afraid about mathematics. We have ensured that we talk it in a way that it's super easy for everybody to understand, because that's entirely the reason we are here. Next up, today I'll go over supervised and unsupervised learning, which are the basic concepts of learning approaches by a machine. But we have like a dedicated session on supervised learning wherein we talk about linear regression, one of the most basic algorithms out there in machine learning. How do we predict that straight line out of those points? The entire session is going to be about that, and you're going to hands-on code the LR mechanism. My bad, sorry. Once we've talked about linear regression, next obviously comes the logistic regression. These two come together at all points of time. We are also going to talk about distinct logistic regression algorithms that are out there. So it's going to be pretty much like a deep dive, not just going over what the concept is. Moving forward, we'll talk about the other more common learning algorithms, which goes beyond linear regression. And once we've touched all the supervised learning algorithms, we'll tap in the unsupervised algorithms and talk more in detail about recommender system, which is kind of the core right now. Netflix, Spotify, what else? Everything out there is recommender system. Amazon, everything is recommender system. So we'll talk in detail about the recommender system in session 6. Session 7 is going to be a deep dive into neural networks. Now, this is where the journey for deep learning also starts. So if you are somebody who is kind of passionate towards learning how NLP or computer vision works on a broader scale, you first need to get stuff sorted on the neural network side. And this is going to be the session for you, wherein we talk how exactly neural networks depict and mimic the brain neurons. Deep learning essential is going to obviously be after that. And session 9 is going to be a specialized session on computer vision. So people who are interested in how object detection works or how this Waymo is doing wonders, that is going to be the session for you. NLP is when we give the systems input as a human, and we expect the system or the machine to understand that human language and respond as if a human would do. And session 10 is all going to be about natural language processing. And then comes the LLMs, the topic of the decade. 2024 was the year of LLMs, now projecting towards AI agents. So LLMs is going to be session 11. Session 12 is RL. People who already know the basics of machine learning and deep learning will definitely agree with me that today people are shifting towards reinforcement learning and the frameworks in that direction, because it's the hype, because it's something good there. That is all about the 12 sessions that we have planned. So I highly recommend you to be active on Discord and Sun Devil Central. These are the two primary platforms wherein we're going to be posting all about our workshops and the agenda. And then there also exists Instagrams. Let's get back to today's session. Okay. So as I said, today's session is pretty much going to be about the foundational information about machine learning. And today's agenda is going to cover what is the hype. I talked about it in the AI at ASU event as well. Why AI systems everywhere? Then we're going to talk about the landscape. People know AI exists, machine learning exists, and deep learning exists. But what is the relationship? That is what we're going to clear today. We're also going to learn about the learning process in AI, which is pretty much obvious, but let's understand it from a machine perspective. Then we are going to talk about learning approaches, how essentially a machine learns, which is the core concept of machine learning. Moving forward, we'll talk about deep learning, supervised learning, unsupervised learning, and the evolution to LLMs. And at the last, we can touch the new frontiers that are added to AI, all these new buzzwords like NLP and computer vision. One note point here that I want to give to everybody. Today's session is pretty much basic, so it's not going to have coding hands-on experience for you guys, because we are having all the information laid out there so that the basics are sorted. But once we progress and advance to the upcoming sessions, we are going to hands-on code on Google Colab. It's the simplest way out there to set up. Just log in with your ASU or any other Gmail ID that you have. There's nothing more to it, and it acts like the best coding solution out there for a orientation like this. Moving forward, so I want to make this fact out loud that you are already an AI user. Why I say that? Alexa, Siri, Netflix, Spotify, Amazon, everything is pretty much using AI at the bedrock of it. But when we talk about all of these advanced systems, we must understand that these are dense networks. There's a lot of computation that is going behind it. There are n number of techniques that are implemented to get out even one feature and making it working for the clients out there. But for people like us who want to develop features like that, it is very important to understand the core of machine learning first, because then only we can get to the level of developing such advanced features and implementing all of these algorithms. So since we are like already an AI user, it gives more of a motivation kind of a thing for us to understand how essentially a machine works and how essentially a machine learns. But before we dive into that concept of learning and approaches and everything, let's first understand the AI landscape. As I said, people know what is AI, what is ML, what is DL, but they don't know the right relationship between it. Or they might know, but they just don't know how to quote it well. So this simple diagram should be on the top of your head whenever you're talking about machine learning, deep learning in general. And there can be n number of frontiers that are added to it later. But this is going to be the core framework. So artificial intelligence sits on the top. It is the entire goal wherein we want to give human-like intelligence to the systems or the machines. That's pretty much about AI. And then how you do it, you essentially make the machine understand those concepts. So the process of learning for the machine is machine learning, obviously. But what we do in machine learning is instead of giving it this for that, or if this, then that, that rule-based approach, we don't do that. We give out machine n number of possible ways, and the machine itself figure out the way forward. So it's like giving a child a book, not a book, let's say lots of books with pictures, and just letting it be like that and asking that child to figure out by giving certain examples that, okay, if you saw one light there, what is this? You see that kind of parallelism that we are drawing? That is machine learning. So we give out examples to the machine and let it be on itself to learn. And that iterative process of learning is called machine learning. So AI is the goal to achieve is machine learning. And then there's another subset to it, which is deep learning. And I could possibly say it as a specialized form of machine learning, wherein the process that goes under the hood actually mimics the brain cells, the neurons. That is why we call it neural networks and deep learning, because there are a number of layers to it. So it's a subset of ML which utilizes neural networks, and the multiple layers together process the data. So you remember how we gave that child the pile of books and we told that child once that, okay, this is the image of a cat and this is a cat. We gave examples, right? What if we leave that child on its own and let it be like that and ask the child to learn himself, like, what is it? That figuring out mechanism when mimicked by a machine is deep learning. So the next time anybody thinks of AI, ML, DL, just think of this concentric circle landscape. Goal is AI, to achieve is ML, and when you advance that goal by adding layers to it and no examples is deep learning. But we'll talk in detail about how deep learning works. Let's first understand the concept of machine learning. And even before that, let's understand how a typical AI learning process works. It's pretty much simple as how humans learn, but since it's a system, it has different angles to it. So think of it, again, I'll take that example of the child having the pile of books. The child had the pile of books. There was data. And in the same way, we need data collection in the machine learning process. We need loads and loads of data. The machines are not as smart as humans. They can never be. Humans are way past that. And just because of that, the amount of data that is required by any said machine to understand, to learn, to recognize is hundreds, millions, thousands. Like, I can't even stress. The more you give, the better the answer. That's the trade off. So data collection is the first part. Then we do training. It's the most computationally expensive step out there in a learning process. It's like giving all the data to the model and now asking it to understand one by one. Now, since we're talking on the level of those millions of data sets or millions of data entities, the compute time is obviously going to be more. So training is super expensive. And it is kind of like an internal system wherein the model learns in itself that, okay, this was the image, this is the output I got. If I see an image with a tail and a pair of ears, it might be a cat or a dog. Or if I just see ears, it might be humans. So that is what goes behind the training process. And then comes testing. It's like an exam for the model. You gave the data, you gave the training, and now you want to test it out. So this part here is where the testing scenario is involved. So you don't give the data the same training samples just to see how well it performs on an unseen piece of data. And since that is the notion behind it, we want our models, why we do that is because we want our models to be generalist and not memorizing and galloping all the information. We don't want that if it sees certain particular type of image, so it classifies it as a cat. No, we just want it to understand all the features that are associated with a cat and then test it with a new image and see how does it perform. That goes behind in testing. And then once we are confident enough that yes, the system is doing good, the answers it is making is correct, human validation gives super nice answers, it is good to go, then we deploy it to the real world, putting it into the action for real world applications like, let's say, a spam filter, put it out on the email, classify things as spam or no spam. That is the kind of implementation in the real world applications that we do once this entire learning process is done. Now, since we have seen how that thing progresses, let's understand how essentially machine learns. And for that, I would want to quote this simple example of cat picture classification. How do we identify that a particular, let's say, image is of a cat or not? Has ears, has tail, has whiskers, and let's say also is covered in fur. Four basic things, right? And then the list can go on, but this is something that we can essentially start off with, four basic traits. So let's say we have this identification checklist right with us. Thousands of sample passing this right, and it is going to a good training session. Everything's working well. But then there are unexpected cases. What if there is a species of cat that does not have pointy ears? Our identification checklist, point one, failed. That's the problem. So there's this species of Scottish fold. I'm not sure if I am quoting that right, but yeah. Uh, does not have pointy ears. The ears are folded. The machine will not understand it well. It will fail. Or what if, let's say, our cat, the picture of a cat does not even have fur? Another checklist item failed. So these are like the unexpected cases that can happen in the real world scenario. But what if the scenario is set right, but the assumptions that we need to make or the items in the checklist are quite challenging for us? For example, everything's right, the cat is there, all the four features are there that we are talking about, but the image is in a shadow. We can't see the whiskers. So even the feature is there, we can't spot it. So again, a rule has failed. And then there could be a fourth scenario wherein the cat has a tail, but not a long tail. So you see how there's a role play of unexpected cases and challenging assumptions that are always behind challenging our checklist, whatever we make. So that kind of problems occur when we go through the rule-based approach. What we talked about is the rule-based approach. We specified if else, then, if you understand the normal coding syntax. So there are multiple if blocks. And what if all of it fails? The model cannot adapt to the new features. It's pretty much falling and failing. What is the problem right here? We got that right. But how do we solve it? We solve it through an approach called the photo album approach. Now, instead of measuring features and putting it in a checklist, what if we give millions of photos to the machine and ask it to understand, now see what are the features on yourself? I'm not helping you. Just store all of these images, just identify the distinguishing patterns, take into the consideration what n number of features can be there. So you see how the model will figure out on its own now. And then, since we have those millions of records as data, the model is fed with lots of data. So it's going to improve itself and work around it on its own. So this photo album approach is the core of machine learning. And I don't want you guys to confuse it with all the scenarios wherein we just give images. It could be textual records, it could be tabular form of data, it could be CSVs, it could be labeled data, unlabeled data. For example, there could be the email chain thing that I say. It could be a data of millions of records of emails, and they are classified as spam and no spam, and the machine learns itself what is a spam, what is a non-spam email, and then classifies it on itself. So that kind of approach, wherein we guide the model with some pre-existing data, is machine learning. So we showed thousands of images, we let the model figure out on its own, and then the model improve on its own. So this is the rule-based approach, which is the core concept of machine learning. We saw how machine learning works. N number of records, put it into the system. We have some features out there. We have specified those features. And then we get into the process of classifying those features according on the lines of those features. And then the output is like cat or no cat for the given example that we were talking about. I'll take a pause here before going on to deep learning. Is there anybody who has a question possibly? Yes. These slides will be circulated to you once we get off from this session. Yeah, you had a question.
More number storage we dedicate to train the model, you get more accurate results. So for you to be able to get 100% accurate results, theoretically, you have to fit it in finite amount of storage. Is it not technically possible, or is that not?
So at all point of time, I'll just repeat the question for anybody who did not listen. The question is, to get 100% accuracy, do we want to load the model with infinitely many samples of data and then let it figure out what is the right answer or what is the wrong answer? But that is going to be computationally expensive, right? We can't just have infinitely many records and load it into the system. But another question I have here for all of you is, do we want 100% accuracy? What if it's just an image of a dog in a shadow and it assumes it to be a cat? So we have real world scenarios like that. There's a concept called overfitting and underfitting that we're going to talk about in the later sessions, wherein we essentially talk how models need to be at the right balance of training and testing. But having said that, to answer your question in like simple terms, 100% accuracy shouldn't be the goal when training models, to be very honest, because you want your models to be generalist. You want them to understand the core concepts and not ignore such situations wherein the real world scenario might be something else and you're quoting it something else. That being said, the more of it will be taken up in the latter sections. Okay, did I answer your question well? Is there anybody else who has a question? Okay. Good to go then. So we talked about how machine learning works. Input, then we had the features listed out there in a form of a checklist. And then we have the classification mechanism, the algorithms working at the back end, doing XYZ things, and then giving us the output. Let's not get into the XYZ things right now. Let's just understand the concepts. Then comes deep learning, which is a subset of machine learning. What if we ask the models to do everything on its own? I wouldn't give you features. I want you to understand everything on your own. And then in that typical scenario, it will utilize something on the back end called neural network, which mimics how the processing works in the neurons in the brain. It figures out on itself when I give a photo of a cat that, okay, this has ears. Lots of images have ears. Maybe cats have ears, and that too. And then this particular image has a long tail, and then lots of images have long tail. Cats have long tail. But then let's say after 200th record, I see the type of species that I showed, a short tail or technically a no tail. Then the model has another feature in its hand and tries to scout for more options or more examples or records wherein that particular feature is present. So you see how we are not guiding the model. It is having the brain of its own. It is having the consciousness of its own. It is having the intelligence of its own. That is where the feature extraction and the classification part, putting together that checklist and classifying the images, is happening on its own. That is essentially how deep learning works in simple terms. So deep learning also involves neural networks, as I've been saying, and neural networks are like complex networks having multiple layers. Just to put down into an example that we are talking about how neural networks work in this particular scenario, we have the first layer, which might learn how just simple edges work or how simple colors are there into the play of the pictures. And then we might have the middle layers that just combine these edges to form shapes like eyes, ears, tails, noses. So you see how the model is figuring out on its own. And then there might be just last layer or the final layer, which is combining all of those features together and then telling me, yes, the image that you gave me is a cat, or no, it's not a cat. So that is how the deep learning process works. And this is basically a distinction between deep learning and machine learning out there on the screen right here. Okay. Before we go forward, any questions on deep learning? Yes. It could be anything. It's just easier to understand in the form of how a pile of books or pile of photos would work. That is why I'm quoting this example. Oh, sorry, yeah.
So it's like an automation of learning for a computer?
Kind of, yes, because mhm.
Learn something that is technically incorrect. Like identifying pictures of cat, like learning itself, and it falsely identifies a dog as a cat. Would there be any way to like undo that like error? Like,
So,
against that?
okay, think of it from this perspective. What if you have a baseline task at hand, right? You want to classify the images as cat or no cat. So the data that you'll technically have will be somewhat on the lines of cats, dogs, and whatsoever species are on the similar lines. So here's the thing, the model itself iteratively learns. There are complex things that go at the back end, how these things work. But to understand it simply, the instances of the model getting to know a cat rather than a dog is going to be much more when we are particularly dealing with the task. So if we think from that perspective, if you have, let's say, just 12 or 15 images of dogs in a data set of 100,000, it's pretty much obvious that the model is going to itself learn how that particular image is of a cat. But it's just a simple example. There are more complex things that go at the back end. there are systems how and networks how the model itself learns that why this is not a cat and why this is a dog. And there are other complex systems as well that go into the picture, which escalate the scope of this learning right now. So yeah, but just the core idea that I told you. Anybody else? Yes. So we can decide the layers because there are different types of neural networks that exist. We can decide the layers as to how we want to train and how many layers we want to put in the picture. If we want to, there are scenarios wherein we also don't want all the layers to get into the perspective of working. We just want to drop out a few layers. That is also possible. So it's a combination.
Cat for this example.
No, this is just a baseline example. It could be much more advanced than this. Okay. We do? Yes.
Can you be a bit louder?
Yeah.
Could you be a bit louder?
Is the question like you don't get how the oh okay. So neural network, as I say, just picture it as how the neurons work in the brain. There are different elements to it, and all of those elements work together to get to one consensus of decision. That is pretty much the entire concept of neural network. When we combine all of these together, you could essentially think of it as a deep learning network wherein the model works together to get one answer. But these are complex things. We have super basic things like linear regression and all as well. It's not that complex, not mimicking the neural network thing. It's just simple maths how things work. So. Mhm. That is why we are going to talk about it in the next session. Yeah. No, it's all good. It's all good. So the idea right here is just to learn what are the terminologies and how things work, but to get into the nitty-gritty details of what's the science behind it, why are two functions working together to get this particular output, or why is this particular setup like this setup of a neural network. All of this we're going to talk about later once we advance in the sessions, and we have dedicated topics for it. Yes, another question? Mm-hmm. Yeah. Mhm. So to put the question out there, the question is, let's say, for example, we have the data as all the images of black colored cats, and then we have instances of white color cats. Is it going to say as the output that it's not a cat? Definitely yes. But then how do we ensure that this does not happen? There are two aspects to it. A, when we talk on the level of simple models at the base of it, the core concept that if you give in trash data, it's gonna give out trash answers. But here the data is not trash, it's essentially cats. So another angle that you can add to it is more extensive that you be with the n number of types of images that you put in for the cats, the better the model is going to be at learning. Because essentially at the core of it, we the humans are putting in the data. And then there are advanced topics wherein there's a concept of reinforcement learning, wherein You give the task to the model, and then you give the feedback to the model that, yes, you did a good job, this is the right answer, or no, that was not the right answer. That's the core of reinforcement learning. And that is how we can ensure a model does not messes up with what we have. And then when we escalate to pretty much to the level of models wherein they're trained on humongous sorts of data, that happens essentially on the lines of once we advance, because the data that we are training it on is super huge. So there are mechanisms and techniques and practices that go behind the curtains to ensure that whatever models that we are building, whatever systems that we are building, is good enough to do the classification task or whatever task is at hand.
How model training black hat, don't give yes to black hat model. Any other, not just like that.
Yes.
Can you fix it? Yes, by adding more data. Right, and then retraining the model. Not necessarily. If the model is available for everyone, they can download it and then. So you learn more about this, how to do all of that.
Yes. Yeah. Question.
That you say you add more data, is there a way to remove that correct data?
There's no way to remove that, to be very honest. The core idea that I feel here is that some sort of incorrect examples is still okay, because the idea of generalist and not memorizing the core aspects is what we follow with training all these machine learning algorithms. But yeah, there's no mechanism to undo that. You can just have more data to do the model to understand the core underlying patterns and then figure out if it's a cat or not a cat, for example.
When you have, let's say, one incorrect image out of, let's say, 1,000, because it's learning patterns, the idea is that it will learn the correct pattern even if there is one wrong image using the 999 images that are there.
Yep. Anybody else? I can't hear you. Can you be? What are the images for? The end goal is to classify if it's a cat or not. Yeah. Okay, yeah. Technically, no, because the model is understanding on itself. You remember how we gave that initial identification checklist? So we set the parameters. For example, let's talk in terms of house price prediction. I have the data of, let's say, a particular county, and I have it in the dimensions of what is the square foot area of that house, or what is the location like, or what are the amenities like, or how old is the house. You see how we have different segments to it? That is the identification checklist that we were making. But if we just leave the model on itself, this is the data, dump it in, it learns on itself the patterns and figures out on itself. So there's no intervention from our side, essentially. That is how it works. But it's more to that. When we get to the deep learning concepts in detail in one of the session, we'll talk more about how exactly the landscape looks like for deep learning. Anybody else? Yes.
So I believe when you say a particular model, a model is open to the public,
Mm-hmm.
which is, any set of people who know how to train a model, which is essentially open source, like one of the open source models.
Mm-hmm.
Despite it being trained by so many different people from different backgrounds, different beliefs, why is, and it being, it training itself further, deep learning, basically, why would it still be biased towards one side of ideology? Why does AI?
Now, if it's technically dependent on the data.
Yeah.
If the data is, can you have a data that is unbiased?
Very hard.
Very hard. So that's the answer. The more unbiased data that you try to put it into the data set, that is how it is going to learn. And the number of data samples that are across all the spectrum, let's say you're looking at cats right now in this problem, right? So you have white cats, brown cats, whatever, all possible varieties of cats. But let's say one type of cat is only 10, which is Westall is like 1,000. This number of samples that is there is still less. And it can't learn because it is trying to learn patterns. And then it has to understand how exactly the images or different types of cats look like, right? And then that is how it builds a pattern recognition. It's basically pattern recognition underneath, right? So in order to do that, you need unbiased data to have an unbiased model, but that's very hard. So that is where a lot of other mechanisms come, which you learn more.
So practically, it's never possible to have an AI that has the proper method, as long as human.
It's hard.
It's hard, but we're getting there. And then to answer it, just to crisply tell everybody, all of the things depend on the data. So whatever you feed in, if it's good, you expect the model to be good. If it's, then the model is also going to be non-good, like unsatisfactory. Yes, we have one more question. Yes, yes. And that is where the layers get dense, and that is where we escalate the entire landscape. Those are even complex systems than just a few couple layers.
In one of the sessions, I think that she showed, the computer vision session, you're going to train a model that is going to predict 100 different types of outputs. So that is a very less number. So there are models that predict more than a million types.
To quote an example to this, we all pretty much see how Waymo works here, right? There's a science behind how Waymo works. How itself it's figuring out where to stop, what is the object in front of me, is it small enough, is it a human, and all those angles. So yes, there's a possibility to have the model understand much more complex landscape wherein we have not just the cats, but n number of other things as well. Anybody else has a question? Yes.
What was trained more of that?
What do a?
Giving it some kind of data to predict, and based on how the model predicts, like what metrics it will have to predict the given data. I think you'll learn more about
Yes.
the next session. We are jumping into the next session right now.
Yeah. So it gets a little complex when we talk about what knowledge the model has acquired, which goes beyond the scope of what we're learning right now. But yes, the model acquires some knowledge, and how it is stored in that model, how that model takes it forward and applies it to the new instances of data that it sees. That is pretty much what we're going to talk about in the upcoming sessions when we talk in particular detail of all of these topics. Yeah, I think let's move ahead now. So this is how we saw how typically a deep learning model works. It's like giving eyes to the machines itself and letting the machines figure out on its own that you are on your own now, and now figure out what is the feature and how you want to go about it. Having said that, this is one of the most basic topic out there. Whenever everybody and anybody starts to learn machine learning, they study this topic called supervised learning. You recall how we gave that child a pile of books, or we gave that model a data of millions of records, and we told the model that cats have ears, cats have whiskers, cats have tail, cats have this, that, and all of it. That is where we are labeling the data. We have different features to the data. And supervised learning at its core is like having a supervisor guiding you through the process of learning. So we have the content out there, we have the features and the data out there, but that supervisor is making you understand how to spot the right patterns, or what features to take into the consideration, and how the mathematics and science go beyond the scope of this. So that is supervised learning, when we learn from the labeled examples. And the simple algorithm behind supervised learning is that we give in the data and corresponding labels. For example, we give in a data of millions of records of email, saying if this is the fashion of email, it's a spam. If this is the fashion of email, it's not a spam. And then you store it into the system, and the system itself learns that, okay, now this is a new piece of data, and it mimics the pattern that was there in not a spam kind, so it's not a spam. So it essentially learned from a baseline foundational data that was labeled, and it mapped the correct inputs on those lines, following some sort of algorithm out there, which we are going to talk about later. There are different types of algorithms that exist under supervised learning. We'll talk about it in detail. So once trained, now this model knows that if a new example comes in and if it mimics the particular old pattern, this is the output or the label that I need to quote it as. And we use this particularly in house price prediction. We use it in fraud detection. We also do use it in sentiment analysis. Let's say I have a data of news headlines or news articles, and um, the news articles in the data are following some particular fashion or having some particular type of words that are used. And then we can label it as good, bad, positive, negative on those lines. So how the pattern is learned, and then how it mimics an output, how it maps that mimicking pattern, and then how it takes the output forward, is entirely supervised learning. But what if we do not have this all the spectrum of labeled data? What if the data that we have is super random, and how we left the model to itself to figure out? Now the data is all messy, and I know that it is like some sort of data, let's say some transactional data, but I don't know what are the angles to it. I don't know what segments of buyers are there. I don't know how does it work. That is essentially unsupervised learning, wherein the model itself finds the hidden patterns. And there are different algorithms in this as well, wherein we form clusters, wherein we do some sort of work, but we'll discuss that later. Let's just understand what unsupervised learning is. So here, the initial data has no categories or correct answers. You remember how the email data had spam or no spam? Nothing of that sort here. It's pretty raw. And since that label is not there, we do not give an algorithm any sort of example that if this is the case, then that is the answer. The model needs to itself figure out. And the only instruction in this case that we give to the model is analyze the data and figure out on your own what interesting or what similar you're finding, and then see what is the answer that you want to give out. And what is the goal right here is the algorithm just goes through the entire data one by one, finds natural relationships, and just organizes the unstructured data into meaningful groups. Let's say, I'll talk in detail about this example, but yeah, primary goal right here is to find the underlying similar pattern and structure. Let's understand this with an example. What if I want to find hidden patterns in a transactional data? I have this customer data of some e-commerce company, let's say a fashion brand, and I know the tendency of buyers from the data. And how can I group them? Let's say there are luxury shoppers, people who do very few transactions, but the ticket size or the purchase amount is very high. So you'll put that under the category of luxury shoppers, right? That will be entirely another set of cluster. And then there will be some people who just go after sales and just do purchases during sales. They'll have a peak there. And there might be certain set of audience or certain set of customers that just do seasonal buying, like just particular seasons of peaks and troughs, and then the customer data moves in that fashion. But there will also be a regular shoppers category that no matter whatever the scenario is, people in this category, they'll keep on buying. You see how 4 different distinct categories are possible, and there are n number of other categories that are possible as well. But these are the 4 basic things that we could think of. And how Just by talking, we formed clusters of its own, that luxury shoppers is one cluster or regular shoppers is one cluster. If we can understand this way, so can the machine. We give out this data to the machine, and the machine itself figures out that, okay, high transaction amount, luxury shopper. Or let's say just having peaks of purchasing in winters, seasonal buyer. You see how the model itself thinks in the lines or on the lines how a human thinks, that this is one cluster, that is one cluster, and just organize it there. So we started off with unlabeled data. We did not tell it that if there's high ticket amount, that is luxury shoppers. It figured out on its own. That is unsupervised learning, wherein the entire concept of learning happens by finding the hidden patterns in itself. I'll take a stop here. Does anybody have a question? Yes. So prompts come into the picture when we talk about large language models, which is pretty much the aspect of NLP. You're talking to the models. That is something that was not possible some years back. Machine learning is not a new topic. It's been there kind of like more than, I can't even stress on the number of years now. But why are we learning it till this state is because even we advance to the topics like LLMs, AI agents, computer vision, and all of those things, still at the core of it, there is a pattern how a machine learns. And that is why we essentially learn machine learning. So to answer your question, no, prompts is not how we're communicating to the model right now. We're talking in terms of data, which could be textual data, billions of records of data. It could be images data. It could even be video form of data, but that's much more advanced. So it could be any form of data, multimodal. But prompting happens when we escalate the model structure and architecture to a very advanced level. Yes. So there are different algorithms. For the people who did not listen the question properly, the question right here is that how model scans through the data, right? That is what you asked. So the model understands the patterns and the hidden insights through algorithms. And that is why we have different algorithms like linear regression, logistic regression, k-means clustering. We do have classification problems as well on different tangents. That is happening through the help of algorithms, but at the core of it, everything happens through this learning process that we learned about. And then in detail, we'll talk about each of the algorithms in the next sessions that are planned beyond this. Anybody else? Okay, let me just see the time. Now coming to the evolution of LLMs. What we see these days, ChatGPT, Gemini, Perplexity, Claude, all of these are large language models. The concept of machine learning models, algorithms, now pictured at a much higher and an advanced scale. So since we are talking about large language models, it is pretty much obvious that the architecture behind the scenes is pretty vast. It's dense combinations of layers. It's different sorts of communications that's happening at the back end. But how this evolution happened? So we started off somewhere from machine learning that we relied on the humans to put in that identification checklist that we talked about, the feature extraction, and we defined the important variables that we talked about, as in the example of cats, right? We did identification analysis. We put together a checklist that if these are the features, then it might be a cat. So we have the intervention of humans to define the important variables and the important angles that could be to the different data. And then because all those identification checklist is put into picture and we have clear rules, now the model works towards making a decision on itself. So there's like a clean, well-organized structure, but it is still happening at a very small scale. Moving forward, we move towards deep learning, wherein the model itself learned on its own. We did not have any intervention. We did not do any effort to tell the model these are the important features. The model itself analyzed and sifted through the data, and it itself learned that if these are the patterns, then it might be a cat, or if these are the patterns, then it might not be a cat. So deep learning scenarios, they were very good, and they are still till this day very good at tasks like image classification, because there are a number of features involved in it. But what happens here is that it's still underlyingly, it still depends on the foundational data that we are talking in the scope of it. We are still feeding the data with correct answers. What if, let's say, let's go back in time, and 2010 probably, or even before that, we have vast corpus of data on the internet. Let's just feed it to a model and let it figure out on its own. Yeah, it will be very complex for the architectural layout to be laid there in that sense. But what if the model does that? And that is where the large language models come into the picture. That is, they learn from vast sorts of data, they learn from messy texts, they learn from all the code out there for people who use Claude and GPT and Cursor. So it learned from all of those sources, and itself it trained on all of these data records, and now can perform a wide variety of tasks. So you see how Claude, Perplexity, ChatGPT, and all of it, they're specialized at one task, right? If I'm doing research, I'll use Perplexity. If I'm coding, I might use Claude. And if I'm just uh, wanting to polish my emails, I'll possibly use ChatGPT, right? So there's something out there that's good at some particular task. But there's a scenario that all of these models can particularly perform all of these tasks well. GPT can write code for you. Claude can make the emails better for you. So these models are more of a generalist kind of approach, wherein they operate on a wide variety of tasks and are also good at some specific tasks if they are trained on such specific data snippets. Um, Large language models started off with text and now are advancing towards other forms of data that we put into the picture. So the entire focus is that we generate new content, and we do it by interacting naturally, and we give it a very human-like experience. I talk to ChatGPT, and it's essentially like I'm talking to a friend in itself, or like to an assistant who does the job for me. So that is how we went from just the basic machine learning to something of an advanced topic like deep learning. And now we've shifted our base towards LLMs, and we're going forward. But before closing, I want to make you all understand two distinct frontiers that are added here: NLP and computer vision. So we remember how I talked about the concentric circle landscape: AI, ML, DL. Now there are two added frontiers to it. There's much more to it, but let's just stick to these two. Uh, so when we involve machine learning and deep learning and talk about some intelligence in the forms of text and now even speech, so it's like it's interacting in a way that a human would talk or understand the text. That's natural language processing. You see how even if I put some gibberish out there in ChatGPT, even if I do not put it in one language, it figures out just as a random human would do. So that is where the entire concept of understanding the language by the models comes into the picture, and that natural language is being processed by the models, and it is giving out human-like responses and intelligence. Now, on the other hand, what if we combine the approach of deep learning and machine learning to an extent wherein these taxis like Waymo and everything, they can detect things on its own. If an animal is passing by, it can detect that it's a dog or a cat, I need to stop. Or if there's a signal out there, if it's red, I need to stop. The car is figuring out on its own. And that is where you're giving the vision capabilities to the model, that the model is now capable of seeing itself just as the human eyes would do. That is where the entire concept of computer vision will come into the picture. As we showed in the beginning, we are going to talk about NLP and computer vision in two dedicated sessions as we proceed in advance. So if that is something that interests you, please stick by to that extent. And then let's just quickly recap what we did, and I'll tell you what is next. We talked about how AI is pretty much there in everybody's life every day. We learned how machines learn, what is the core concept behind it, what is deep learning, how machine learning and deep learning has the relationship between AI, ML, and deep learning. We also talked about how supervised learning and unsupervised learning work and how the evolution to the larger language models these days is happening. But what is next is before getting into any ML algorithm in particular, we want to understand the mathematics that happens behind the curtains to implement any um, machine learning or deep learning algorithm. Why we have kept this session? Till this date, there are a lot of people who are not very confident with mathematics, which happens behind the scenes for the models. So it's an effort from our side to make it very hands-on interactive. And from the next sessions, we are having hands-on coding sessions. This session was pretty much basic, understanding the foundational knowledge. But from the next session, you're going to code on your laptop. So I highly recommend the people who have not brought their laptops today get that in the next session, which is happening next Wednesday. Just a heads up once again, this series of ML workshops, it's 12 different workshops that are happening every Wednesday. The location we'll update by Sun Devil Central. It's pretty much going to be the same, right? Yeah, the workshops are going to be here. So it's the same thing for every other session. Um, And then these are the two QRs. On the right side is the all-in-one QR. You'll get to all of our links in terms of SDC, Instagram, LinkedIn, whatsoever out there. We have YouTube as well. We're going to post the recording of this session on YouTube so that it's easy access for everybody. And then on the left, before I take in any questions, I want to tell you all about AI Makerspace. There might be a lot of people right here who know what AI Makerspace is because they have experienced that in the past and must have attended the AI at ASU kickoff event that we had. Just to put it simply, AI Makerspace is like a semester long project cohort. It's like an incubator style setup wherein you come in with your own problem statement and we help you build that project over the course of a semester. We set milestones for you. And in the process, we give you mentorship from our team, which is experienced in AI, machine learning, deep learning, whatsoever. From faculty out there, the faculty from ASU, we have PhD mentors. We also do have industry connections. So if your project closely aligns with some sort of problem statement out there in the industry, that is the scale that we're talking about. And there might be instances wherein you need resources, GPUs, servers, clusters, whatever. We can provide you that, given the commitment is there and the motivation is there. So that's all about AI Makerspace. We have our first session of AI Makerspace tomorrow, which is where we talk in detail about what, how, when, and what we're trying to achieve. So if any of you is interested, please be active on STC and fill out the interest form here. And now I think let's do a quick Q&A before we hop on to food. Um, is there anybody who has a question? Yes. Can you be a little louder? We can't hear you. So if you want to learn, that's the idea. If you want to learn machine learning from the scratch to the advanced, you can just follow along these 12 sessions and you'll be good to go. Anybody else? Who does who? Is there anybody online who has a question?